Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would like to come back to, well, I would wrap up schemes, like to wrap up schemes, with one of the most, important pictures on schemes that have appeared in the literature, and it's actually, so what is our main example? I will remind you what it is in a second. So it was this picture, which I'm going to pull up a little bit bigger now. So I got this from Peter Bellman's website. It's actually really nice. Link is in the description, and essentially there's a little bit of a history of those pictures of those schemes, and this one is the first one historically. So that's the one that I'm going to use. And it turns out that this one, which I'm not going to discuss, is the more popular one. But I learned from this website, and it's true that this one is actually so the other one that I'm going to use is actually a bit younger, and I find it also a bit easier to understand. They're essentially the same, but slightly differently drawn. So this is the one which you usually very often find if you just Google Mumford's drawing of spec ZX, but historically this one is actually the first, so I'm going to stick with that one. Then there are some other drawings. So here's another one, which is like a nicer version of the one from above, and some other drawings on this side. It's actually really, really, really nice. Okay, but anyway, so we want to stick with this drawing. It's the historically first one as far as I know, and it's the first interesting polynomial ring you would think would like to discuss would be maybe ZX. And what do I mean by first interesting? Well, because it's not a field, you actually have some arithmetic going on, and polynomials is what we study in algebraic geometry anyway. So this is like the behavior of polynomials would be the geometry. So the diagram essentially emphasizes the behavior of polynomials in kind of an interplay with the arithmetic of prime numbers in this the easiest possible example. And it's like this Mumford's drawing of a spec that's one at the top. And we draw that over spec Z, which is like the line here at the bottom, right? Spec Z. I have a bigger picture on the next slide. Actually, all pictures I have in this talk are just this picture. So don't worry about it. So we'll zoom in. I can already show you. We'll zoom in a second. But for now, we just stay here. We're trying to understand that picture. So just as a reminder, this picture should show the prime ideals in spec ZX. And what are the prime ideals? They come in 4 different flavors. There is the zero ideal, because the zero is always special, right? So zero ideal is a prime ideal, fine. And then there are the f of x ideals, where f is an irreducible polynomials over z, so integer coefficients. And then there are the prime ideals, so this is where the geometry comes, the irreducible polynomials. And then the primes, which is like where the arithmetic comes, right? The prime ideals just given by the primes. And then those mixtures where you can think of this as being irreducible polynomials mod p now. So instead of irreducible polynomials over the integers. And this is like where the real kind of mixing of arithmetic and geometry happens. And this is kind of depicted here. We'll see that. I comment on that on the last slide. But this is essentially what you're supposed to see. Okay, so let's zoom in. So spec Z, the generic point of spec Z, the zero ideal, a little bit boring. And then 2, 3, 5, the prime ideals here. And this is like a picture, as I said, like we draw one over the other. So this is kind of separate part of the picture. So something like this. And like here, these are like the kind of the images of the prime ideals, and you could think of these guys here as being z mod p, right? So here you have z mod p without the zero. The zero is kind of like up here. Zero is usually kind of the thing up here. So otherwise you have 1 in z mod 2, you have 1 and 2 in z mod 3, you have 1, 2, 3, 4 in z mod 5, 1, 2, 3, whatever, up to 6, and like many points if p is very large. And then there's this funny infinite point. Anyway, so that's like kind of what you should see here. And this is like the generic point in them, which is 0. Or you can think of the generic points as being kind of the QP, if you know what that is. and this generic point, you can think of it as being the characteristic 0 version, like Q. So here's like the characteristic 0 branch, and then whatever the characteristic P branches of this picture. Yeah, and then you have whatever, 1 over 5. So let's look at 1 over 5. 1 over 5 here in characteristic 0. So what is that actually? 1 over 5 corresponds to this polynomial, which really is just x minus 1 over 5, unless you're in characteristic 5. Yeah, so if you're in characteristic 5, this is a bit shit. Otherwise, then it's an irreducible polynomial and nicely normalized. So x minus 1 over 5. And yeah, so you can just kind of track it back. It will be somewhere in Z mod P, whatever 1 over 5 is in Z mod P. For example, 1 over 5 is 3 mod 7. Why? 3 times 7 is like, sorry, not 3 times 7. 3 times 5 is 15, and that's congruent. That's like 1 mod 7, right? 1 mod 7. Yeah, and that's why 3 is actually 1 over 5 in 7. So it hits here this line at 3, and here hits the line at infinity because it's 5. 5 is a bit tricky. So what is 1 over 5 if 5 is 0? Yeah, exactly, it's infinity. It's 2 here and it's 1 here. And this is essentially the irreducible polynomial corresponding to x5 minus 1. Yeah, and this kind of makes sense unless it's kind of very nicely behaved, unless you're in characteristic 5, obviously. And then you have this extra funny thing. Similarly for minus 1, it's kind of the next branch here. So we did 5, and now this minus 1 thing, square root of minus 1, corresponds to the polynomial x squared plus 1. Yeah, not x squared minus 1, the irreducible polynomial x squared plus 1. So this should all be plus whatever. And again, you can kind of track back how it kind of decomposes in those under those various primes. For example, in characteristic 3, this is actually irreducible, so it doesn't really intersect in 2 or 1. It's kind of a new point here, kind of indicated similarly in characteristic 7. But in characteristic 2, for example, x plus 1 squared, yeah, it's really just x plus x squared plus 1 in characteristic 2. Yeah, so which is our polynomial. So this kind of intersects this point twice. That's why it goes like this. And in characteristic 5, you intersect in 2 and 3, because those are the roots now of that polynomial. If you just multiply this out, x minus 2 times x minus 3, in characteristic 5, it would be x squared plus 1. Yeah, and that's why it intersects here in 3 and 2, and so on. It would intersect P somewhere. And this is how you should read this funny line here. So it's kind of could intersect if it's irreducible. There's kind of an extra point that you can't really see in Z mod P. Yeah. And if it's not irreducible, it will kind of factor into something, and for example 3 and 2 or something like that. And this is kind of how you should read this minus 1 and whatever. You could put in another irreducible polynomial and whatever. You would get some line here. It's a higher degree. It might hit a line 3 times or something like that. But this is like how you should read those funny, not funny, but those lines going from left to right. So they correspond to certainly the reducible polynomials and the behavior mod P, which is exactly what I promised you, like irreducible polynomials and their behavior mod P. That's what Mumford is trying to illustrate in this picture. Yeah. So spec Z essentially combines structures with algebraic properties of polynomials. So here we have primes and then whatever irreducibility of polynomials, and you can literally see how global information corresponds to localized information along the primes, right? That's what we kind of did. So minus 1 here, a square root of minus 1, which is like the complex number. How does it actually fit to kind of reductions modulo various fields, various primes? And the only thing I haven't explained is this funny codimension, and we'll do that on the final slide. Essentially, the codimension of a subvariety is how many other things you can put in between, right? Dimension is of how many things your space is built out of, and codimension is you start with some y, let's say y, and you can put a certain number of irreducible things in between until you go to x, and that would be the codimension of y in x. And here you can already see we have this big block, codimension 2, codimension 1 thing, the codimension 1 thing, and the codimension 0 thing, and that's the only thing that's missing here. Oops, that was too far. The only thing that is missing here is the dashed boxes, the corresponding codimensions, the generic point, the 0 ideal. If you want, you can think of this as being Q. And then here you have QP, the generic point of the corresponding primes, which is really just the thing P, which is missing, right? So 1, 2, 3 if you want. 1, 2, 3, 4, 5 if you want. And then mod 5 and whatever. 1, 2, 3, 4, whatever. So these are the ones that are missing. So this is this block. Yeah, the generic points over the primes. So maybe let me just put that in the correct color. So here the generic points over the primes. Here the generic point. And here we have essentially the irreducible polynomials mod z, whatever. Here we had our x squared plus 1 friend here, or whatever. So that's the other one. And then the big blocks is then exactly where they intersect. Yeah, you look at the irreducibly, how they are irreducible mod p. That's what we kind of discussed in the whole video. And that's this picture, this famous picture of Mumford of the spect of zx. Kind of nice. Anyway, this is what I wanted to tell you about schemes, and we then move on with sheaves of modules in this case. And then we kind of wrap up algebraic geometry from there. Anyway, I hope you enjoyed this video, and I also hope to see you next time.